Well, I hope you're ready for this. This is the day when you start feeling like a real chemist. Pretty soon you're going to be able to pick up a bottle of Gatorade and read the content label and say, hey, I know what that is. I recognize that. I could write the formula for that. And then you feel like a real chemist. All right, so let's start out by reviewing what we did last time. And that is to look at the periodic table and say, if these elements formed ions, what would be the charge on the ion? So hopefully you remember that in this column, everything was going to be a +1 charge. In this column, we're going to have a +2 charge. In this column, we're going to have a +3 charge. In this column, they're not going to form ions. In this column, if they do form ions, we'll have a -3, -2, -1, and they're not going to form ions either. Now, we also have some ions that are not found on the periodic table, and these would be called polyatomic ions. The ones we've talked about so far are called monatomic. And that means they have one atom. Mono for one, atomic for atom. Whoops, I was going to write monatomic all over again. Let's write one atom. Polyatomic ions have, poly literally means many. These don't necessarily have many, but they have more than one. So there are a list of 6 polyatomic ions that I'm going to ask you to memorize, and we'll be using them a lot. So let's get those down. You write them down too and start working on getting very familiar with these ions. So one of them is called sulfate, SO4 with the 2- charge. Now what that means is we've got a sulfur, we've got 4 oxygens, and those are bonded together by sharing, excuse me, by sharing electrons. And the whole thing as a unit has a -2 charge. So when we use these ions in compounds, we don't break them up. We just treat it as if it's one unit. More on that later. So this is sulfate. We have carbonate, CO3, which has also a 2- charge. We have nitrate, NO3, that just has a -1 charge. We have phosphate, BO4, that has a 3- charge. So you can see that the names aren't too bad. You can also see that many of them end in ATE. Hydroxide, OH-, does not end in ATE. And then we have one that has a positive charge, and that's NH4, and that is ammonium. So that is a short list of polyatomic ions. There are many, many more polyatomic ions, but these are very common ones, and these are the ones that we will use this year. So make sure you have those in your notes. Make sure you become very familiar with them. All right, let's get started. Now, whenever we put together an ionic compound, we will have to either start with a name and write the formula, or start with the formula and write the name. So what I'm going to do is start with the name, and we'll learn how to write the formula. So let's say we start with a very familiar sodium chloride. Now our first task here is to identify the two ions that are in the compound. Sodium, we know from our study of the periodic table, is Na, and chloride. Now, chloride does not appear on the periodic table. On the periodic table, we see something called chlorine. So here's the first thing that we need to learn about ionic compounds, or any kind of compounds for that matter. The second word, in this case, the negative ion, will usually end in IDE. It will always end in IDE if it's a single element. So remember those polyatomic ions had different names? But for the monatomic ions, we're going to use the IDE ending only for the negative ion. This negative ion is called an anion. We'll get to that in just a second. So this comes from chlorine. Now we already learned, look, just a few minutes ago we reviewed this, that sodium being in the first column on the left in the periodic table has a +1 charge, and one day we learned why that is, because it has 1 electron, and if it loses that 1 electron, then it looks like a noble gas, which is what they all want to look like. It does not become a noble gas, remember. It just looks like one on the outside. All right, chlorine or chloride is in column number 7, 7A, and we learned that that gets a negative charge because it starts with 7 electrons. If it gets that 1 more electron, which gives it the negative charge, then it also looks like a noble gas. So that's what makes it stable. So what actually happens is when you put sodium atoms together and chlorine atoms together, the chlorine steals an electron from the sodium, and now this is happy and this is happy. All right, so when we put these things together, well, first of all, let's do a little vocabulary. This is the cation, and this is the anion. When we write the formula for an ionic compound, we need to write it such that we have an equal amount of positive charge and negative charge. Now in this case it's very easy because we have a +1 over here and a -1 over here. So if we simply put those together like that, and we're using subscripts of 1, we don't show it when it's a 1, but it's there. So if these two ions occur in a 1-to-1 ratio, then there will be no net overall charge because each one positive charge cancels one negative charge. In other words, we have an equal number of protons and electrons in the whole batch of sodium chloride. So that is a good formula for sodium chloride. Now let's look at one where it doesn't work out that way. Let's do magnesium chloride. So magnesium is Mg, chloride is Cl. Again, we've already talked about chloride. We know that has a -1 charge. If you look for magnesium on your periodic table, you will find it in the 2A family. So that means it's going to have a 2+ charge. And now we want to put these together such that we have no net charge. Same amount of positive as negative. So if we have 2 chlorines to every 1 magnesium, that will make that happen. So we're going to have MgCl2. So this has 2 positives. This has 1 negative, but we've got 2 of them. Each one has a negative. So can you see that we have a total of -2 here? If you wanted to draw it as a picture, we could say we have a magnesium ion, we have a chloride ion, we have another chloride ion, and the 3 of them are going to bunch together, and so all the charges will cancel out. Now, this was fairly easy to do it just by looking at it. I'm going to erase the mess I just made up here and show you something that we call the crisscross method for solving these kinds of things. If we have a magnesium 2+ and a chloride, I'm going to write the 1 in there just so we can see it. The crisscross method says that you take, let's go to a red pen here, that you take this number right here and make it the subscript on the other element. And you take this number right here and make it the subscript on the other element. That's why we call it crisscross. And you'll find that whenever you do that and crisscross them like that, you end up with a formula where the total amount of charge is 0. So that just works all the time. So let's look at a few more examples. I think we need to use some examples that use our polyatomic ions. Let's say that we have magnesium phosphate. All right, magnesium is again in family 2A. That means it has a +2 charge. So we identify first of all the ions. Phosphate. Now that ATE kind of rings a little bell in my head, and I say, oh, the ATEs are not on the periodic table. That's a polyatomic ion. So I go look at my list and I find that that's a PO4 with a 3- charge. So if I want to put these together in order to make a compound that has a net charge of 0, I'm going to crisscross these charges. I'm going to write Mg and use this 3 over here. And then I'm going to write PO4, and then I need this 2 over here. That gives me a little problem here because now it looks like I have PO42. So I get around that problem by using parentheses. So I'll put parentheses around the PO4, that's treating it like a unit, and this tells me that I have 2 phosphates and 3 magnesiums. So 3 times 2 is 6, 2 times 3 is 6, so we have 6 positives and 6 negatives, and success. We have a formula that works for us. Let's try another one. This time I think I want to use our ammonium ion. What shall we have? Ammonium, let's make up sulfide. I'm not even sure if ammonium sulfide exists, but it probably does somewhere. All right, so ammonium is NH4 with a +1 charge. Sulfide, let's find sulfur on the periodic table. This I gives me a clue that it's probably on the periodic table. And we find sulfur, which had become sulfide when it became on an ion. And that has a -2 charge, and I know that because it's in family 6A. It has 6 electrons. If I give it 2 more electrons, that makes it a nice stable ion with that octet of electrons on the outside. So I want to write this NH4, and I need a 2 subscript. So we'll do that. And then S, and this only a 1, so I just need a 1 subscript, which is not shown. So that would be the formula for ammonium sulfide. Now one more, just to make a point. Say I'm going to have sodium hydroxide. Whoops. I need to write the name first. All right, sodium hydroxide, Na plus for sodium. Hydroxide is one of my polyatomic ions, like that. And if I crisscross the charges, it's 1 to 1, so I only need 1 for subscripts. Now watch what happens here. I write NaOH. And the point I want to make about this is I do not put parentheses around that. The only time I'll use parentheses is if I have to use them in order to put a subscript on the outside. But since I don't need a subscript here, I'm not going to use parentheses for that. So that's quite a few examples for starting with the name and writing the formula. But let's go backwards. Let's say we have the formula and we want to write the names. So we'll write a few of these down here and say that we have K2SO4. Let's start with that one. And then we can have Na2CO3. We can have calcium, let's see, what have we not used yet? So let's see, where would it have to be? And then let's do something without a polyatomic ion and just say that we have something like that. All right, so going from the formula to the name is probably a little bit easier because we don't have to do any math for that. We don't have to think, oh, where are the charges, what are my subscripts and all that kind of thing. We just have to identify our ions. So I've got a potassium ion and I've got a sulfate ion. Now notice that I did not circle that little 2. That little 2 tells me that I have 2 potassium ions. But the formula for the ion is just K+. The 2 does not belong there. So anyway, this becomes potassium sulfate. And all I did there was name the 2 ions. The cation always keeps the name of the element. You probably noticed that from the examples that I gave you when we were going the other way. The same name that we use for the element, we use for the positive ion, and that's whatever element comes first. The anion is where you change the suffix to IDE if it's a monatomic anion. In other words, if it's an element that I can pull right off the periodic table. Now, for these polyatomic ions, they just have names. So all you have to do is look at your list and say, well, what's the name? And write it down. And that's all you have to do. You don't have to deal with the fact that there's 2 there, because if I have this name and I know the charges on these, I can get back to the formula and I don't need something in the name to tell me that there's a 2 there. All right, so this we have sodium and we have carbonate, so we just call this sodium carbonate. And again, I don't have to worry about that 2 because I know when I put sodium and carbonate together, I need the 2 to balance the charges. And here we have calcium and we have phosphate. And I shouldn't have circled that 2. This is phosphate all by itself. So calcium, phosphate. And then this, if you search your periodic table really hard, you'll find this over towards the bottom part of that first column in the periodic table. That's called rubidium. And chloride we are familiar with by this time. So here's where we have to stop and think, because we don't want to write down chlorine, since that is an anion, in other words, the second one in the compound. It has the negative charge. We don't just use the name that's on the periodic table. We actually change the suffix from INE to IDE. And you'll kind of get the hang of this as you go along. I'll give you a few suffixes. When you go down that column 7A, they all change their INEs to IDE so they sound the same. So you'll have chlorine, fluorine, bromine, iodine, and those become like fluoride, chloride, bromide, iodide. So that's fairly simple. Oxygen becomes oxide, so we drop quite a bit of that term. Occasionally you're going to see something with a hydrogen as an anion, and that becomes hydride. We'll see that once in a while. Phosphorus becomes phosphide. Sulfur becomes sulfide. So there's some good examples of common ones. Nitrogen, nitride. And I think that takes care of pretty much all the common ones that you're going to see. So at this point, you know how to take a formula for an ionic compound and write the name, and you know how to start with the name and write the formula. So these are all ionic compounds. In other words, they're made up of ions. Ions have charges. Now, in the next lesson, we will take some compounds that are not made up of ions. They don't have charges on the different parts of them, but they're sharing electrons instead, and those have a different set of rules. But for now, we'll just use these.